So we have covered how we can detect the different tastes. Now, let's discuss sensitivity of these receptors. Uh, the taste system encodes information about the quality as well as the identity of the stimulus. This is something that we have noticed before. So that means that we have several taste buds, but we don't detect the flavors or the different tastes in the same way. Similar way though, but not quite the same, so we can distinguish them. All right? But the higher the stimulus concentration, sorry, with this, the higher the stimulus concentration, the greater the perceived intensity of the taste. So we have to bear in mind that we will have different concentrations at which we will have a detection threshold over which we will be 100% sure that what we are tasting, basically, to cut a very long story short. But let's realize about something just by looking at numbers. You have all these numbers that I want you to look at here. Salty taste will be detected at a concentration of 10 millimolar. Sweet taste, sucrose basically, will be detected at a concentration of 20 millimolar. But sour will be detected at 2 millimolar. And bitter, remember that bitter is always associated to a potential danger, like quinine and strychnine, which is a venom, will be detected at a very, very low level of concentration. That means that thanks to taste buds and taste receptors, we can detect the most poisonous chemicals at the lowest concentration possible, ensuring this way that we have prevention in case one of these venoms enters the oral cavity and is just about to enter into our digestive system. Bear in mind something, once in the digestive system, once we reach the small intestine, the absorption occurring there will be huge. Okay, and that those chemicals will eventually get into the bloodstream easily, maybe reaching the liver, and maybe enhancing the toxicity of the hepatocytic cells. So avoiding the ingest of any poisonous chemical is a must. So this is the reason why this detection at different concentrations happens like this. Okay, all parts of the tongue, all parts of the tongue are sensitive for all the tastes, but there are some regions that are mostly sensitive for a specific taste, since they have a specific threshold for the detection of a specific tastant. All right, and we have a condition, algesia, that is the perception that happens when the perception of taste is lost. Taste sensitivity actually is lost with age. Okay, so now let's discuss what are the central pathways that enable the processing of the taste information. Okay, let's start by stating that each sensory fiber branches many times, innervating numerous taste buds, and within each taste bud, several taste cells. Now, the electrical activity recorded from a single sensory fiber represents the input of many taste cells. The sensory fibers that receive input from the taste cells enter one particular place that we have to remember, that is the nucleus of the solitary tract. And it will do so through three different cranial nerves. First one, cranial nerve number 7, that is the chorda tympani, comes from the body of the tongue. All right, so if we go now to this schematic representation here, we will have this here. Okay, we go through the geniculate ganglion to the nucleus of the solitary tract. Let's enhance the image a little bit by adding this. We go there and we go here. So basically what we reach is the nucleus of the solitary tract, one particular area, the gustatory area. All right, secondly, we have the lingual branch of cranial nerve number 9. That is for the root of the tongue and the soft palate. So we should have it like in here. We would have it input from here. We go here, okay, and we stand here. And last, we have the cranial nerve number 10, that is the superior laryngeal branch of the cranial nerve number 10 that would go for the epiglottis and esophagus. Remember, the cranial nerve number 10 is associated to the most proximal region of the digestive system. So basically, we would have it here. We go to the nodus ganglion, cranial nerve number 10, and we reach here. So with all of them, we reach this particular area here, nucleus of the solitary tract. So if we look at here, that is the nucleus of the solitary tract, we can be sure that there should be a distribution of the cranial nerves that is topographic. All right, so these cranial nerves will be topographically represented along the rostrocaudal axis of the rostral portion of the nucleus of the solitary tract, that is the gustatory nucleus in here. So that means that each of the three cranial nerves that we have mentioned reaches a certain area. We have a topographic distribution of the places at which each cranial nerve reaches, and that allows us to have a better discrimination from scratch. So we have rostral portion for cranial nerve number 7, the mid region for cranial nerve number 9, and the caudal portion for cranial nerve number 10. Now, the caudal part of the nucleus of the solitary tract receives information from the subdiaphragmatic branches of cranial nerve number 10, which control gastric motility. As I have mentioned before, we can associate always cranial nerve number 10 to the motility of the digestive system. It will be in charge of this motion, in charge of promoting the motor movements of the digestive system, of all the digestive too, up to the second third of the large intestine. Now, interneurons will connect the rostral and caudal portions of this nucleus of the solitary tract. And now, from here, from the nucleus of the solitary tract, where do we go? So basically from here, we have to go upwards. And whereabouts? Well, we will go to the ventral posterior medial nucleus of the thalamus, or in other words, its acronym VPM. This is a place that we already know. This is the place at which neurons in turn project to several regions of the cerebral cortex, all right? So this is like a relay step, you know that for sure. From here, we project to the anterior insula, which is the place where we allocate a primary cortical taste area, the orbitofrontal cortex, which is the secondary cortical taste area, and the hypothalamus and amygdala. So, two places at which we go from the nucleus of the solitary tract, being one of them the VPM and the other one the hypothalamus. From the VPM, we can project to the anterior insula and the orbitofrontal cortex. And how we can summarize this. In this schematic representation that you're seeing here, you have a summary of what I have just said. If we now enhance the image and go to this particular schematic representation, I think that we can understand very well what we have mentioned before. So in here, we see the organization of the human taste system, basically. And here you see the pathway that we have mentioned, okay? We have taste buds from the anterior two-thirds of the tongue, connected to cranial nerve number 7, from the posterior one-third of the tongue, connected to cranial nerve number 9, and from the epiglottis, connected to cranial nerve number 10. The three cranial nerves will reach the nucleus of the solitary tract, all right? This is the place from which we will have projections to the VPM of the thalamus, the ventral-posterior medial nucleus, the hypothalamus, or the amygdala. From the VPM, we should go to either the insula or the frontal cortex, and eventually we will have a feedback back to the amygdala. And this is how we organize the information that has been received from taste buds. If we look here, what we can see are the axons from the nucleus of the solitary tract, reaching the VPM, and from here going to both the insula and the gustatory cortex, that is the frontal cortex.